We call numbers such as 1, 2, and 3 integers. That just means we can counter them upwards or downwards. 7 is an integer, -16 is an integer, even 2 million is an integer. Sure, it might take a long time to count to 2 million, but it is theoretically possible. A number we cannot count to, however, is 2.5. No matter how hard we try, we will never count to 2.5. Therefore, we do not consider 2.5 an integer. What 2.5 is, however, is a rational number. A number which can be represented by an integer divided by another integer. For example, 2.5 is 5 divided by 2. They look like they fill the entirety of the number line, right? For example, the rational numbers with 10 as their denominator will look like they fill up the number line to some extent, and the rational numbers with 100 as their denominator will fill it up even more, and the rational numbers with 1,000 as a denominator will fill it even more finely. And if we continue on and on, it looks like we can conclude that every single number we can think of on the number line can be expressed as a rational number. That is what the famous Greek mathematician Pythagoras thought. He had a cult known as Pythagoreans who believed that all numbers on the number line are rational. They can all be the fraction of two integers. They also had some very strange rules, such as never eating beans because apparently they contain the souls of the dead. But from a mathematical point of view, Pythagoras' belief was pretty interesting. However, there was one number that disproved all of his beliefs. Ironically, it arises in his own theorem, the Pythagoras Theorem. According to the Pythagoras Theorem, if we have a right-angled triangle, the sum of the squares of the lengths of the two shorter sides equals the square of the length of the longer side. According to the theorem, if the two shorter sides had a length of 1, then the longer side should have a length of √2, a number that when squared gives the number 2. That should mean that there exist two numbers a and b which divide to give √2. But eventually, after trying, they ended up disproving the fact that any two numbers can divide to become √2. Somehow, the rational numbers covering the number line so well have managed to miss this number. The Pythagoreans try to keep this a secret for as long as possible, but eventually a guy called Hippasus leaked all of this outside. Some anti-Pythagoreans burned down the house of Pythagoras and other Pythagoreans, and chased Pythagoras to the worst possible place he could be chased, a bean field. Pythagoras chose to be stabbed to death rather than running through the bean field. And √2 is not the only number they have missed either. √2, √3, cube root of 5, and cube root of the sum of √2 and √3 are all examples of numbers which cannot be expressed as the fraction of two integers. But you can notice that they all solve polynomial equations. Remember, polynomials are any expression that looks like something plus something x plus something x squared plus something x cubed plus so on. It becomes an equation if we try to make it equal 0. We call these numbers that solve polynomial equations algebraic numbers. These numbers fill in much of the gaps between the rational numbers. Note that even though it may not feel like it, much like the integers feel like they are floating in a sea of rational numbers, each rational number will feel like they are floating in a sea of algebraic numbers. That is how many algebraic numbers there are. Yet still, there are gaps. Numbers such as e and pi cannot be expressed as the solution to any polynomial equation. They are not algebraic numbers. We call numbers like these transcendental numbers. The proof that they do not solve any polynomial equations are very long and complicated, and were only discovered as late as the 18th century. It is possible to go on and on, deeper into the levels of the numbers, such as computable numbers and so on. But overall, the total name of the numbers we know and love are real numbers. Every number that can fit on a number line is a real number. Just pick a random point on a number line. You don't know if it's an integer. Chances are it's not. You don't know if it's rational. Chances are it's not. You don't even know if it's an algebraic number, even though it is likely not. However, you can perfectly guarantee it is a real number. They are the full set of numbers, right? However, there still are equations that no real number can solve. Take a look at the equation x squared equals -1. As you can see from a graph, there is no real number for which this is the case. The square of 0 is 0, the square of positive numbers are positive numbers, and the square of negative numbers are still positive numbers. There is no reason for there to be a solution. Mathematics carries on just fine without there being a solution. But what happens if you make it so there is a solution? Or rather, two solutions, as it is a quadratic equation. Well, obviously, neither of these solutions can be a real number, so we have to invent a whole new system of numbers. We will call them imaginary numbers. Note that they are called imaginary numbers simply because they are not real numbers. They do not have a place on the number line. You cannot call them greater than or less than a real number like 1, 2, or even pi. We will define one of the two solutions to a quadratic equation, I, due to the square of negative x being the same as the square of x. It is easy to see that negative I is also a solution. Any real number multiplied by I gives another real number. 2i, 5i, negative square root of 7 times I, pi I, ei, any real number you name, multiplied by I to get an imaginary number. It was the mathematician Argand who came up with the idea of letting the imaginary numbers go up and down while the real numbers go left and right, intersecting at 0. This kind of geometric interpretation of complex numbers is called the Argand diagram or the complex plane. And finally, what happens if you add a real and imaginary number together? For example, 2 plus 3i. This is neither a real number, nor is it an imaginary number, as it is not a real multiple of I. It is what you call a complex number. For example, the complex number 2 plus 3i can be represented on the Argand diagram as over 2 and to the right of 3i. We can come up with more and more complex numbers, such as 7 plus 2i, 3 minus 4i, -4 minus 2i, -1 plus 5i. Any combination of real and imaginary numbers will give a complex number. Later in the series we will come back to the Argand diagram, but for now we will focus on the complex number itself. Just a simple introduction of I has suddenly introduced all sorts of numbers, and the best part is, it's all mathematically consistent. Apart from divided by 0, it is possible to add, subtract, multiply, divide any two complex numbers, and even better, every single polynomial has at least one solution. But for now, you hopefully have a clearer understanding of what a complex number is. The next video will be about how we add, subtract, multiply, and divide complex numbers. So in the meantime, make sure to like this video and subscribe to my channel so you do not miss my next video. Bye!